Bismillahirrahmanirrahim. So we started talking last time about the comparison between distant vector and link state routing protocols. And we said that for distant vector, each router sends periodical route updates. And through these route updates, each router will calculate the total distance between this router and all other destinations. We'll calculate the total accumulated distance between itself and all the other possible destinations. So it calculates what we call the distance and then the direction that it has to take in order to reach that destination. So in order to forward a packet all the way to the destination, in distant vector routing protocols, I need to figure out the total distance to that routing, to that final destination, and the direction. For link state, however, link state is different. Each link will be advertised independently, and all the link states should be propagated throughout the entire network. So each router will end up having all the states of all the links in the network or in the autonomous system. Okay? And then it runs the routing algorithm in order to figure out the end-to-end path. Okay, so that's the fundamental difference. So based on that, so for distant vector routing protocols, routes are advertised as vectors of distances and direction. As we have talked about last time, each router will calculate a routing table, okay? And during the update, it incorporates all the routing table in the message update and then uses the broadcast to send it to all routers around it, to all the neighboring routers. Okay? The routing table contains two important information in addition to some other information. The two important information are, first, the total distance, and second, the next hop or the direction that I have to take. So for example, this router, in order to reach this LAN, for example, it needs to calculate the total distance, which in that case, in terms of number of hops, will be 2. And it needs to go through this router in that direction. So it needs to go to that direction, and it needs to have a distance of 2 in order to reach to this LAN. Okay? Based on the fact that each router receives information from the neighboring routers only, okay? So the view of any router is restricted to the information that it gathers from the neighboring router. Therefore, each router in general will have incomplete view of the network topology. So I do not have any information about the entire topology of the network. All I need to know is that the distance between me and any final destination is X, and in order to go there, I need to take a step towards a certain direction. But I have no guarantee, I have no global view about the network. For example, I can take a first step towards a certain direction, and then the router next to me may actually send me to some other wrong destination or some other wrong direction, in which case I will not reach the destination. So I do not have a global view about the entire topology of the network. I only have the information about the links that I'm attached to, and then I have one distance between me and any possible destination in the network. But I have no idea about how the topology looks like. The other difference is that generally I use periodic updates. So as we have gone through an exercise last time, we said that each router will form a message update which contains the information in the routing table, and then it will use broadcast to send it to the neighboring routers. Okay? And that happens every 3 seconds. Periodical, every 3 seconds. Each of the routers that will receive this message will have to calculate the incoming message update compared to the routing table that it has, and then update any new information based on the incoming message update. Okay? And then this router, after 3 seconds, will again incorporate the routing table in a message update, and then it will send it forward as broadcast. Okay? So we'll keep doing that gradually until we reach to a state of convergence, in which case all the message updates contains no new information to any of the routers in the network. Okay? So this is the state of convergence. We'll talk about that in details later. So we keep gradually and periodically updating the routing table of each other until we reach to a state that the message update that any router receives contains no new information. So assuming that the topology of the network is fixed for a period of time, this state of convergence is guaranteed. Is guaranteed. Okay, so we will indeed reach this state of convergence. The link state, as we said, is fundamentally different. Each router in that case will have a complete view about the entire network topology, because I have the individual link state of all the links in the network. So each link state, for example, this router, it will actually calculate the link state on this link and this link and this link. Okay? Will form a message that contains the link state of all these links, and then it will again broadcast. The main difference here is that this router will not have to calculate the distance. This router will repropagate the same link state to all other routers in the network. It doesn't have to calculate anything. Okay? So this is the main difference here. In distance vector, these message updates, each router that receives it will have to calculate the distance compared to the distance that I have in the routing table, and update the routing table, and then in the next cycle I will have to formulate a message from the routing table and send it forward. In the link state, it's different. In the link state, all the link states of all the links will have to propagate to all the routers in the network before any calculations happen. We see the difference here? So in that case, this router will know that it has that there is a link between router 2 and router 1, and this link has a state of X, has a certain state, and will get the information about this link and all the other links in the entire network. Okay? In the link state case, I do not have a routing table that contains distances and direction. I don't have that. I have a link state table. So I have a big table with all the links in the autonomous system and the state of each link. Okay? So based on this link state table, I will calculate the end-to-end path. So I know that in order to reach to a certain destination, I need to go through this link, and then this link, and then this link, and then this link, and so on. So I have a global view about the entire path that I have to go through in order to reach to the destination. Do you recognize the difference, the main difference? Because this is really fundamental. In that case, updates are not periodic. In general, updates are not periodic. Why? Because if the link state gets propagated to the entire network, and then I only need to report the link state if it changes. So if the link state changes, then I propagate the new state of this link to the entire network. Okay? But in the case of distance vector, I have to periodically incorporate all the routing table in the message and send it forward, regardless, even after conversions. After the conversions happens, I have to do the regular job. I have every 3 seconds, I have to incorporate update message with all the routing table information and send it forward. And I have to keep doing that periodically. For the link state, I only need to report the state of the link if it changes.
For the router and the middle option, to get the information from the routing table of R1 only, sir?
Right. No, routing table, router 2 will get routing update from router 1 and router 3 and router 4. Yes, the R1 will send a message update to router 2 about this link and this link. Each router knows by default, and we'll talk about that, each router knows by default the links that it's attached to, it's directly connected to. So this link and this link, router 1, once you start the interface, this interface and this interface, router 1 will know the state of these links because they are directly connected to R1. So initially, that's the only thing I know. And we'll talk about these different scenarios. So it's very important to realize that routing updates in the case of distance vector is generally, because there is an exception that we will talk about. Generally speaking, it's periodic, and each routing update contains incomplete or localized view of the topology of the network. Okay? Whereas for link state, the change is not periodic, and eventually each router will know the global topology of the entire network. The links, this is the link state. For the link state, router 2 will have a link state database, will not have a routing table. Each router will contain a link state database. Link state database will have all the links and the state of each link. At any point in time, the algorithm, in order to calculate the end-to-end path to any destination, it will have to parse this table and then give me a complete path. So you have to go through this link and this link and this link and this link in order to reach to the destination, because I have a global view about the entire network. So that's the main difference. Another categorization for the routing table or routing protocols is classful routing protocol and classless routing protocol. And of course, this we discussed extensively in 455, so I'm not going to go through this in details, but for classful routing protocols, I don't have to exchange subnet mask. So in that case, of course, we all know what subnet mask is. If you don't know, you need to review the material in 455. So this, in classful routing protocols, I do not have to exchange any information about the subnet mask. Why? Because the IP address of any network indicates the class. And from the class, I can figure out the subnet mask without having to exchange it. For example, 172 is already class C. Okay? 172 belongs to class C. And class C indicates that the subnet mask is 24 bits. So in that case, the routing protocol will not have to exchange anything about the subnet mask, which is /24. It doesn't have to exchange that number. It only needs to send the IP address of the network, or the network address. And from the network address, the routing protocol will figure out the class, and based on the class, it figures out the subnet mask. Because the subnet mask is important, because I have to always XOR the subnet mask and the IP address in order to calculate the network address. Because the network address is the one that I should be able to look up in the routing table. In the routing table, I always use the network address, not the host part of the address. And we discussed that in 455. For classless routing protocols, in that case, routing protocols, they have to exchange the subnet mask. So in that case, the IP address of any network does not indicate any class. For example, I can use the same IP address that I used here, 172, but in that case, I use a different subnet mask because it's classless. So this number does not indicate any class. So in that case, the routing protocol will have to exchange the IP address and the mask. The IP address and the mask. What the routing table will do, before it looks up the IP address in the routing table, what it actually does is that it has to XOR 27 ones with this IP address. And then the result will be the network address. I use that network address to look up the routing table. So I have to do this operation before I look up the network address. For classful, the same thing. The only difference is that for classful, I can know the subnet mask without having to exchange it. Because the IP address, this highest, this leftmost byte indicates the class already. So 172 is class C. Okay? So that's another categorization of routing protocols. So some routing protocols will use, like, for example, distant vector, and they can support classless or classful or both. Okay? So conversions is a very important state, which is defined as when all the routers have a routing table which is consistent. Because consistent doesn't mean the same, because you cannot have all the routers have the same routing table, the same content. That doesn't make sense. Okay? But consistent means that any message update that gets exchanged between the routers do not contain any new information based on the information that this router already has. مفهوم ده؟ So any message update, whether distant vector or link state, okay, any message update contains no new information based on the information that I already have. And this is the case for all routers in the autonomous system. This means that this router already, for distance vector, this means that this router already has the correct distances and directions to all the possible destinations in the autonomous system. For the case of link state, this means that all routers will have all the states of all the links in the entire network. ماشي كده؟ So that's what we call the state of conversions. This is important here. So the usually distance vector routing protocols, they suffer from slower conversions compared to link state. Although, as we have discussed, link state routing protocols, each router will have a global view, right? Whereas for distance vector, each router has incomplete view about the topology. However, because of the periodic update, because of the periodic updates in that case, and because for each update, the router will have to calculate the distance and then put it in the routing table. And then in the next cycle, it picks up all the changes in the routing table and send it. So you can imagine that if we're talking about update every 3 seconds, for example, every 3 seconds you have to receive something and calculate. This is the key. You have to calculate something. And then put it in the routing table. And then in the next cycle, you pick up the change and then you send it forward. So in order for a change in the network to propagate all the way to the entire network, it takes time. Right? Because for each time you have to receive routing update and you have to calculate. This is the key. You have to calculate. In the link state case, you don't have to calculate anything. Right? You just forward the link state. You just forward the link state. So in a matter of milliseconds, all the routers will get the link state of the entire links, of the entire topology, right away. So you don't have to calculate every time. And that's the key. And you don't have to do it periodically. So whenever a router receives a link state change, it propagates it asynchronously, not periodically. You see what I mean? So whenever I receive a link state update, I will forward it right away. So based on that, all the routers will get the link state of all the links in the entire network very quickly. And then the calculation happens one time at the end for the entire path. Okay? So based on that, the convergence is faster in the case of link state, faster compared to distant vector. Why? Because distance vector, every time I have to do incremental update and calculation, incremental update and calculation. Whereas for link state, I propagate the incremental change quickly and then I calculate once at the end. ماشي? Another important parameter is what we call a metric. And a metric is very important parameter through which I calculate how good this distance or this end-to-end path to the final destination is. So the metric indicates whether this route to the end destination or the distance to the end destination is the best or there is better. So this is a value used by the routing protocol to determine which routes are better than the other. And the metric is a generic term which can be represented using any phenomenon, any variable. For example, rep version 1 and rep version 2 uses a metric as the number of hops. So the distance between me and any possible destination is simply the number of hops. Okay? So the distance between router 2 and the address 172.16.3.0, which is this one, is 1. So you have to go through R1 and then you reach this LAN. The distance between this one, router 3, and this LAN, the distance between router 3 and this LAN here is 2. Why? Because I have to go through this first and then this. Okay? So the routing table will contain this distance or the metric, and it has to contain something else, which is the direction. Should I go this way or this way? Okay? So in that case, the second piece of information that should be in the routing table, because this is not the routing table. But the routing table has to contain one more piece of information other than this, which is the direction. In that case, the direction is this way. Is there any other alternative for the metric other than the number of hops? Yes. Why? What is the motivation? Why the number of hops is not necessarily the best way to calculate the distance?
Maybe it's a short path, but the quality.
The quality of the links. Bravo, Alik. So, so the shortest path between this router and this router is, in terms of number of hops, is this. But in some cases, assuming that there is a link here, in some cases, it's better for you to go through the longer path and you will reach faster. And we all know that, right? We experience it every day. For example, we commute every day through North Road, for example, right? In some cases, in some instances, the North Road is totally blocked. So you keep going through some, a longer route, and you reach faster, right? Because the shortest path that you can calculate is not the best, because it's currently blocked or is currently highly loaded. That's why the metric doesn't necessarily have to be the number of hops. For the first routing protocol that we will study, which is RIP version 1 and version 2, they use the number of hops, which is simple. It's very simple to maintain and calculate. However, it's not necessarily the best way of calculating the metric. Okay? May include the bandwidth. Okay? So, for example, I have this link has a bandwidth which is like ADSL. It uses like a very low speed ADSL line. It's 56 kilobits per second. This is a very old version of ADSL. But this one contains T1 connection, which is like 10 megabits per second or something like that. Okay, so in terms of number of hops, this one is the best, right? But in terms of bandwidth, it's better to go this way because this way has a larger bandwidth. Okay, so the longer route, like for example, sometimes we have to go through a shortest path, but the shortest path, like very narrow streets and stuff. So the possibility of traffic jams in these narrow streets is high. And we prefer to take the highway, even though in terms of distance the highway is much longer, but you reach faster because the highway is wider and the possibility of traffic jams in the highway is less, and so on and so forth. Another possibility is the cost. The cost represents the cost that I pay. For example, if you you get charged per usage time. So if you go this way, you might pay more, but if you go this way, you might pay less, and so on. So the cost might be another possibility of the metric. The delay is the delay that I will take. Bandwidth and delay can be interchanged because they have one-to-one relationship, more or less. Hop count, of course, and the load. Load is different from bandwidth. Sometimes I have very large bandwidth, but this large bandwidth is already taken. 90% of it is already taken, which is the example that we talked about. We go through the highway, but the highway is full of cars, so the load on the highway is much higher. Okay, so the load represents real-time information. Bandwidth represents theoretical bandwidth on this link, but not necessarily the real-time condition of that link. We see the difference? So there is a difference here. Bandwidth is simpler because it does not represent current information or real-time information. Load requires that you have to keep track of the load on all the links, which is hard to maintain. So you have to keep track of all the load in real time, which requires more maintenance, more overhead. But the bandwidth, it's easy to know the bandwidth before you start the transmission, because you have information about the lengths, so you know that this link is T1, this link has a bandwidth, theoretical bandwidth of whatever, and so on. Reliability. Reliability talks about the probability of this link going down. The probability of this link going down. For example, this link is highly reliable because the probability of that this link goes down is like 0.0001, 10 to the power minus 5 or something like that. Why? Because this is connected to, like, for example, AT&T. So this link is highly reliable. Whereas this link connected to مثلا أريدو, the reliability is 10 to the power minus 4 and so on. So the reliability of the link gets incorporated into the metric. One thing I have to say here is that the metric is not represented by only one of these. It could be a combination of all these. Okay? So this is, for example, the rep chooses the shortest path based on the hop count. So rep uses the simplest one. Hop count is the metric. Whereas OSPF chooses the shortest path based on the bandwidth. Okay? And for example, EIGRP uses like bandwidth, delay, and load and reliability. A combination of all these. So we'll talk about all these things later. Okay? So the metric field in the routing table is indicated here. So this is the metric. So as we said before, the routing table contains two very important pieces of information. In order to reach to this is how you read it. In order to reach to this destination, this is the distance between you and this destination, and you have to go via or through this network to the next hub. So this is the distance, and this indicates a direction. So those are very important pieces of information. Okay. Of course, there are some other information like the time. This is the freshness of this route, and the 120. This is called administrative distance. We'll talk about all this other information, but the most important two is the distance and direction. Okay, so this is the distance, and this is the next hub or the direction. Okay, كده? And this time indicates the last time that it was updated. So this means that 26 seconds ago. This was updated 26 seconds ago. And this is this indicates whether it's serial or it's Ethernet and so on.
This distance is based on the hop count?
Yeah, the distance in that case is based on the hop count.
So we can calculate the distance based on the
bandwidth, based on whatever. So this could be a number, but normally even for because bandwidth could be like float number, right? Real number. Could be like or cost or these kind of. But usually they try to calculate it in such a way that it becomes an integer value. Okay, we will see how.
Doctor, so now each routing protocol has a specific matrix that it follows. It
Right.
is not related to the application that it's using.
That's a good question. There is, in some cases, a variation how the routing protocol calculates the metric. For example, EIGRP uses by default delay and bandwidth. However, the non-default case incorporates also the load and reliability. So there is slight variation here. And it's up to the designer, the network administrator, to include the default values only, or to add on top of that the extra parameters as part of the metric. That could be related to what application is running. So that's what I was saying. So rep uses the hop count easily. EIGRP and IGRP uses bandwidth, delay, load, and reliability, whereas OSPF uses sometimes cost or bandwidth. Okay? And this depends on Cisco's implementation. So that's the metric. Another important phenomenon is what we call load balancing. Load balancing. Sometimes load balancing routing protocols, when you have a certain destination, sometimes you can reach that destination through multiple possible routes, right? If there is one route which is the fastest or the best, I shouldn't say fastest, the best. Again, this is based on what? Based on the metric. Right? If there is one route to the final destination, which is the best, then you use that route. So what if you have n possible routes, and then you have more than one route with the same metric, or with the same final distance? Which one do you take? Well, some routing protocols will say, I will use one of them. I will use one of them and that's it. For example, I can use the fresher one. The fresher one. So if one of them is more recent, I will use the fresher one and that's it. But some routing protocols, particularly OSPF, uses this phenomena of load balancing. So what it does is that it says, okay, I will consider both routes. So when I send a packet, I will consider two routes. For example, if I want to reach to that PC here, I can reach this way or I can reach to it through this way. Okay? If the cost of those two routes is exactly the same, sometimes the routing protocol will say, okay, I will maintain both routes, and again I will zoom out here. In the routing table, I will maintain the two routes. So this reads as follows. This reads that in order to reach to this destination, you have a distance of 1, but you have 2 possible next hubs. So what will happen? The routing protocol will then have to divide the packets. Remember that once we establish the route, we send stream of packets, right? Multiple packets. So in that case, load balancing talks about the fact that you can divide. You can divide the packets that you send. For example, you can send 50% this way and 50% this way. So that's what we call a load balancing. So load balancing talks about the fact that in some cases you may have to maintain more than one route to the same destination. If that's the case, then you have some procedure to divide your packets across these potential routes to reach to the final destination. And that's how you represent that in the routing table. For the same destination, you have two routes. In that case, you have to do load balancing. So you have to divide your packets between those two possible routes. Sometimes routing tables, even if the cost or the metric of these routes is different, they choose to use load balancing. For example, if the difference between the two possible routes is very small, also we can use load balancing. And in general, load balancing leads to, it's a trade-off. It leads to better performance, for sure, because then you can balance out your traffic. It's like you have more flexibility to distribute your traffic across the network. So the end result will be, all the links will be highly utilized, in which case you have better performance. So this is the gain. What's the cost? The cost is the overhead of having to maintain multiple routes for the same destination. So your routing table will grow, and the routing protocol has to be smart enough to support more than one route for the same destination, because it requires some overhead in terms of maintenance. Okay, so that's the overhead. This is the cost, and the gain is, of course, better performance, because then you can distribute your traffic across the network in a fair way, in which case all the links will be utilized. Okay, so this is what we call. So this is the examples of distant vector routing protocols. So we have like three examples. We have REP, IGRP, and EIGRP. So next time we'll go through, we'll start talking about REP first, after a little bit of introduction about distant vector again, and then we'll go through EIGRP and we'll know the difference between the two. Okay?